Hi, this is Track B AI Foundations, and today we are looking at part 3 machine learning. And this will be the first part. We are going to look at part 2 as well. We'll also look at reinforcement learning as part of upcoming weeks, but today we are purely going to focus on supervised learning, unsupervised learning, and the core algorithms that are used in this. And at the end of this session, we are going to look at what does a learning loop look like, where does the model come in, what does the loss look like, what is an optimizer, and why generalizing to unseen data is the whole game, because we might over optimize the model for training data alone, but it has to generalize enough on unseen data so that it can predict correctly when it is put into production. We'll look at some core algorithms and that will differentiate how a good engineer or even a PM reaches for a right algorithm given a data set, and why overfitting reflex needs to be trained for product managers and engineers is something that we are going to look at. 95% accuracy, when somebody says that or a data science team says that out very aloud, we need to ask out, hey, is it on the trained data, or is it on the held out data, or is it on validation data, or is it on test data? And one of the metric that we will always try to focus on is precision versus recall. And if we have encoded the wrong metric, we'll always find wrong answers when it goes to production. uh, we'll look at some examples on how to choose the right metric also. Yeah, then we'll have to put a gate feasibility with data. We always need to ask, hey, do we have the required labels, and are they clean, are they representative of the data, and finally, do we even have the license to work on this data? And here is the roadmap that it looks like. We'll start with the first three paradigms. We'll look at supervised, unsupervised learning models today. Reinforcement will look in the future, but very clearly the learning loop will be discussed today. The supervised learning will look at regression and classification models, the core algorithms that we could use, how to avoid overfitting, and how to evaluate them. Unsupervised learning will look at clustering as the primary algorithm here, and we'll look at dimensionality reduction, why we should reduce the dimensions when necessary and when it can be done. Yeah. From the preemp's perspective, we are going to look at how features and data decide what kind of algorithm we will use. And when somebody says we have lots of data, they are usually wrong. We need to ask these three core questions. Hey, are they clean? Are they representative of the actual problem that we are trying to solve? And is the data licensed to be trained for a model to be trained on that? So that's what we are going to look at today. Let's start with classifying what type of algorithms we can use when we have the right form of data to solve a particular problem. And that typically comes from what signal does the model learn from. Yeah. And one question that sorts all of the classical ML problems. So imagine we have a clear labeled data. For example, you have emails coming in and you have clearly classified for a long time which of them are spam, which of them are not spam. So we have a clearly labeled data, and if a model needs to be trained on this set of inputs and labels, we typically use supervised learning. It typically means that we are supervising with certain labels. When we have input data but we do not know what are the hidden patterns or format of data, we typically use unsupervised learning because there is no labeled data here. Typical examples include your segmentation, your topic clusters, identifying anomalies, and so on. Reinforcement learning is an exception to these two, because here what we are doing is we are learning from rewards instead of learning from input labels or on its own. Here a human or another system rewards based on the action taken on a particular environment. If a robot or an agent takes the action of moving forward in a grid of maze or in a maze, uh, we reward saying that whether it's in the right direction or not. If it is in the right direction, we reward it in positively. If it is not in the right direction, we reward it negatively. So all the examples include gameplays, robotics, reinforcement learning through human feedback, or model training where Initially, the LLM models were trained for providing the right answers. All that happened through reinforcement learning through human feedback. So, supervised models are good when we want to predict the right answer from examples. Unsupervised learning when we want to find the structure and patterns in data without a clear labeled output. Reinforcement learning is good when we want to learn by trial and error to maximize the reward. Many of the cases that we look in production are typically supervised because we know for sure that hey, from taking an input we have a y output. Your support ticket classification, your um, default versus not default, your prediction of cricket scores, your prediction of housing prices, everything comes from supervised models. And secondly, are unsupervised models when we know that what are the important features, but we want to typically learn how to identify the patterns, we go for unsupervised. Finally, the reinforcement. Yeah. Ideally, whenever we have the required data, exhaust data, we should always start with supervised. Look for the labels. If it is available, use supervised. If not, look at unsupervised models. Ultimately, if we want a system that needs learning on its own through rewards and punishment, then we go for a reinforcement learning. And this is what the whole loop looks like. Typically, we get the training data, then we train a model on top of that to calculate the loss. How far are our predictions from the actual values? And then we, in the last track A of part 3, we looked at this. We calculate the gradient of loss, and then we optimize. That is, we calculate the gradient descent. We nudge the weights in the direction that lowers the loss towards the bottom, and we update the weights. And the model trains for one more epoch, if I can call it so, or a cycle, and it keeps doing the predictions until our losses minimize, and we have optimized the whole model for predictions. And throughout this uh, track B, we are going to see this loop again and again. And that's what we are going to look at as long as we go. We're going to look at models, the predictions that come out of it, the loss that we calculate, and it passes through optimizer to lower the nudge the weight to lower the loss. Yeah. So anything where people say that hey, the loss plateaued or we are changing the learning rate, everything comes from this diagram. That brings us to supervised learning. We know supervised learning as something where we have the input data, we also have the labels, and we would like to build a model that is generalized enough so that given a new data, it predicts the label or outcome seamlessly. So there are two types of problems that we typically solve through supervision. One is regression versus classification. In regression, we are looking at a continuous number, whereas in classification, we are saying, hey, is it a spam or not? Is it a um, type A ticket versus type B ticket? Is the user gonna default or is he not gonna default? Will India win? Will India not win? That kind of categorizations. Yeah. So what is common between both? They both have tabular kind of a data, and we are typically measuring them for their success by the error size that they produce. So we use either root mean squared error or absolute error, mean absolute error. And this is for regression when we are trying to predict a number. Yeah, housing price, the demand in a particular place, the expected handle time for a ticket, the lifetime value of a customer. All of these are regression where we are trying to predict a number. Whereas in classification, where we are trying to predict a category, whether it's spam or not, the ticket type, whether it's fraud or legit, we typically use precision and recall. And if either of them do not solve for us, we use the a combination of precision and recall called F1 score. We're going to look at this in the coming slides. Will predict churn is unspecified until you say will they, which is classification, and for how many days, where we use regression number. Yeah. So sometimes these both are used in combination as well. And in supervised learning, there are not just one or two models. There are multiple algorithms that we could use to build those models. Algorithms are nothing but models in this case. We could use linear or logistic regression, we could use gradient boosted trees, we could use support vector machines. So all of these serve one particular purpose. Yeah. So let's look at how are we using each of these, and when do we need to reach for these models compared to the others. So we'll start with linear or logistic regression and go from there. Yeah. Imagine there are various houses in a particular area, and you are trying to predict the rental uh, value for a particular property. So based on various features or parameters like size, bedrooms, the age of the property, the location score of the property, and so on, we would ideally typically draw a line like this, which is a regression line. And whenever a new point comes, we will calculate the price of that house based on that line's distance. So given an x point, we calculate the y score. So that's how the equation looks like for linear regression. And in classification, it typically happens that given a set of parameters, we want to calculate whether users would default or not, whether it's a spam or not, whether it's a fraud or a legit call or not, and so on. So in this, we use a logistic expression which helps us decide whether it will fall here or fall here. So there is a sudden shift as the value approaches this x value. It will either stay on the left or on the right. So we need to ensure where will the classification fall, so that we are able to predict whether it's a spam or not a spam, and so on. And the good thing about linear and logistic regression is we get these weights, so we know for sure which of these parameters have a higher influence on the outcome. Imagine age was x1, income was x2, previous visits was x3, and so on. And the higher the weight, the higher the influence of that feature on the outcome. Yeah. Imagine these were the weights. So it clearly says that income has a higher weightage when it comes to classifying whether the user will default or not on a particular loan. If the income is high, user will typically not default, he will be on 0. But if user had a lower income, the chances that he will default on a particular loan is higher. Yeah. Similarly, in a regression line also, imagine these are the weights and size. Yeah. Higher the size of a particular home, the higher the rental value or the purchase value of a particular house. And this is very evident from when we draw the line and silence the other parameters, it becomes very evident for us. And we reach out to linear and logistic regression because we need a fast and explainable baseline. It's easier to explain from these parameters. We always start here. If it is not helping us solve the problem, we go to advanced models. One good advanced model is a decision tree. Imagine you have a lot of data and they can be categorized into two paths at every junction by their labels. For example, if you want to approve a particular loan for a particular customer, we pass them through this graph. Hey, is the income greater than 50k? Yes. Is the existing debt less than 20k? Yes, approve. Yeah. If it is no, then deny. Similarly, other way around. So what does a decision tree help us do? It creates a flow chart with all the parameters and helping us navigate this tree one at a time. But the problem with this singular tree is that it overfits the data always. That is, it tries to fine tune this based on the training data. So when test data comes, it really becomes hard for us to predict the right values. But what is the good outcome of this? It has clear demarcation on what these groups are. Yeah, it has a very clear demarcation. And random forest solves the previous problem. Here we said it will overfit the data, and random forest does the opposite of that. So what does random forest do? Given a training data, it creates slices of data. It creates a certain groups of data from this large data, and it trains individual decision trees. And then once the decision trees are ready, it takes the averages or majority vote of these decision trees and finally creates one decision tree from which the prediction can be done. So that's why this becomes really good, and it's is more improved over on top of your decision tree. And this is the reliable default on top of decision tree because it is hard to misuse and rarely embarrassing. Yeah, a sensible first serious model on rows and columns of data. And gradient boosted trees is the uh, sota the state of the art algorithm for tabular data now, because in gradient boosted trees what we do is we are trying to boost the gradients faster using frameworks like XGBoost, light gradient boost models, and so on. So what this does is when we start with a simple model and we compute the residuals for that line, yeah, how far are these dots from this line, and we train a tree to fit the residuals, and we do the predictions. So the curve has changed. Now we calculate the new residuals, and we have reduced the error. So the errors keep reducing as we keep going forward with many trees. So this is a much more improved process or algorithm over your random forest alone. And this is why it became the state of the art algorithm for tabular data. Yeah, it adds trees one at a time, each fitting the residual mistakes of the ensemble so far. So the error shrinks step by step and helps us achieve much more accuracy. And this brings us to k nearest neighbors. Many a times we want to predict if a particular pattern exists in a particular data without us knowing um, whether there are labels or not for a particular data set. So to identify those patterns, typically what we do is we do a clustering or identify the nearest neighbors. Yeah, so what k nearest neighbors is, stores the training data and at prediction time finds the k nearest points and let them vote on average. Yeah, it'll find the k nearest points to a given point, and that's how the k nearest neighbors calculation is done. Yeah, what this helps us is group all the elements into proper structures, and support vector machine is also a classification algorithm. So this is a classification, or indirectly it's a clustering unsupervised kind of algorithm that we are using. Yeah, and if you remember, we spoke about embeddings and retrievals, which happen to follow a similar structure. We put all the points in the embedding database or vector database, and closest points are considered as the next predicted token there. Support vector machines work when we want a clear margin of classifying two elements or more elements. In linear versus kernel SVM, if it is linear, it's a straight line typically. In kernel, we draw boundaries, and it could be two-dimensional and three-dimensional, where the boundary need not be a straight line. Yeah, this is beautiful on clean data for smaller problems. For larger problems, it becomes really problematic. It doesn't work because there is never a clear separation like this with large margins. That is where neural networks come into play. These are weights stacked as layers that try to determine their own features. Unlike here, where we know what features are, how to use them, and so on, here they learn the features on their own, and the inputs could vary. It could be an image, it could be audio, it could be text, it could be code, it could be any of this data. So what we are trying to say is, instead of tabular data, if we have any other structure, neural networks are best models to be used here. You know, if you have tabular data, go back to your tabular structure algorithms, in which case we have supervised, unsupervised, um, algorithms like your linear or logistic regression, and so on. But if you do not have the structured input data to provide, use neural network. Yeah, you do not have tabular data, use neural network. The layers of weighted units transform from input step to output step, and that's how we are transforming them. We are learning the weights. Yeah, and these become the useful representations instead of hand-made features, saying that what features we will use. And we will typically use them when the input is unstructured images, audio, or text, where the features must be learned. overkill for spreadsheet shaped data. Yeah, do not use them. If it is tabular, please go back and use the other ones, not neural networks, where it usually loses to gradient boosted trees because they are much more adaptable to that kind of data, and they provide a much more cleaner explainable data. Though gradient boosted trees are less explainable compared to their decision trees, it's still better compared to your neural networks. So when you give an image and it says prediction score is high, it has learned the features that it needs to classify an image by. For tabular data, boosted trees usually beat deep learning very clearly because the data is tabular, and drawing your um, um, decision trees or random forests on top of tabular data with clear if then conditions becomes very easy for them to win. Yeah. Deep learning is typically for unstructured data, and that's the central battle that we are trying to fit, is the underfitting versus overfitting. Underfitting says that, hey, I've not generalized enough to predict the outcomes. Overfitting says I have overfit the model to work on the trained data, and it hasn't generalized enough to predict the validation or test data correctly. Yeah, so every model lives on a spectrum. The goal is the sweet spot between too simple and too complex. So underfit has high bias, overfit has high variance. Yeah, so generalization is the goal that we are trying to do, and that typically means bias variance trade-off that we are trying to do. Yeah, why is underfitting has high bias? It basically says that the model is too simple because we haven't fit it properly enough. It is too simple, and hence it'll have high bias for a particular data. So like it's like fitting a straight line to a curve. Many of the data will not be tagged correctly. Overfitting, high variance, because its model is too complex. It has memorized the training data, and it includes the training data's noise as well. It's good at training but terrible on the new data. Yeah, so the whole product manager's job is to identify that sweet spot. How can we go between the two extremes of either underfit or overfit? And that that bottom pit on a U shape, which has the lowest variance, a decent bias, or sorry, uh, where it has the lowest loss. That's a sweet spot. How do we arrive at is something that we need to discuss with data science team and agree upon. And when somebody says, hey, we have achieved 95% accuracy, we need to ask, hey, have you done that on the training set, or is it on held out data? Held out data could be your validation data, or it could be your test data as well. So overfitting a model on a training set could give you 99% accuracy also, because it has learned all the in and outs of that training data. Imagine us attending an exam, and us learning only the questions that are going to come in the exam. We haven't learned the concepts. We only learned the last year's question paper, and this year we sit for the exam and the question paper changes. Will we be able to answer? Ideally, no. And that's the problem with training and testing. We have been trained on last year's exam question paper, but not on the actual um concepts. So if there is a new test that is given to us, we will ideally fail. So training a model is also something very similar like that. We have to train generalized enough that if a new test paper is given, we pass even on that. And that's like the perfect demo. It will fail when it meets real users or real questions. Yeah, and we never judge a model on the data it is trained on. Yeah, because generalization is the goal. We need to evaluate it properly. We do the training, we do the evaluation or optimize the um, parameters and weights based on the validation set, and finally test it. Yeah, we do the testing on a third set, which is test set. Yeah, we could also use cross validation, which is training and validation. We could do cross validation, or we could split the data into multiple sets and train and validate on one test data, and test it on another test data, and take the averages and see if it is really working or not. We capture out on the held out truth. Is it on test data or not? No peeking, which typically means that, hey, we never show the test data are the test data does not leak into the training and validation set. Test data has to be separate. That's what we call by no peaking. That brings us to data leakage, the silent killer of great offline numbers. If information from the future or from the answer leaks into the features, the model looks brilliant but then fails in the production. Future info leak, we are saying that, hey, any test data that leaks into the left side, which is the train and validation data set, that's like a data leak for us. It answers in features, it's too good offline, but when we start hunting, when we hunt, we shouldn't be celebrating. Yeah. So here is a good example. I like this example. Imagine you have churn prediction that you're trying to build, and you have a variable called account closed date. That's a giveaway that a particular outcome would be churned, and that's one variable that we should not include. That's the data leakage that we are talking about. If you include this, we always know that, hey, it's a predictor. So this becomes the biggest predictor of whether a customer churns or not. So if a customer has gone away but doesn't have a close date, does that mean that customer doesn't have the required this? Ideally, no. He might be churning, but a date might not have been captured. And that brings us to the important topic of the metrics. How are we going to evaluate if whatever we have built is working fine or not? Typically, when we have classification problems or we have predictions coming out, what we need to do is we need to calculate two things. Hey, am I able to precisely or accurately give the answer? How accurate have I given? That is calculated to precision. And am I able to recall all the correct answers correctly or not, which is recall. So there are costs associated with each of this, and these metrics help us balance those through F1 score. Imagine if that there is a cancer screening happening using a machine learning model. You need to ensure whether you'll accurately classify, that is correctly capture people with cancer correctly. False alarms cannot be raised. But in recall, it is also important that you do not miss any of the people coming for cancer screening. Yeah, totally two different. How will you classify for cancer screening? We should never miss a particular person. That's more important. Even there could be false positives, that's okay, but we should never miss a particular person having cancer, because the cost of going wrong is very high. Fraud and safety, all these are expensive errors. Recall cannot be missed on that. Whereas in spam, it's okay. If you're not able to precisely capture certain things, it could leak, but you should never be able to say, hey, particular mail is spam or not, and so on. So of the two things that we flag, precision and recall are totally different things. We need to say, hey, of the things we have flagged, how many were right? That's more important for precision. That is precision. Of the real cases, how many did we catch, which is more important for recall. This has high cost, or this has accuracy problems. The trust factor builds here, trust factor breaks here. So F1 balances both, and how much of these should we target is a metric, or a decision that product managers need to take. And that brings us to the third section of today, which is unsupervised learning. There are no labels given to us. The goal shifts from predicting the answer to finding a structure or a pattern in the data. So typically it starts with clustering. You have a data, you want to identify, hey, what patterns exist. So we group the data together with similar characteristics. And dimensionality reduction, where we are saying that, hey, 10 dimensions might not represent or provide the right might not represent the labels correctly. This could be for labeled data as well, but this is more unsupervised, as in we are trying to understand which of the dimensions are actually supporting data or exhaust versus not supporting the learning. So dimensionality reduction, where you reduce the dimensions, it could be used for that. um, Clustering typically happens through k-means and dbscan. That's what we looked at. For example, segmentation of data, topic discovery, deduplication of data, or anomaly detection, all that happens to clustering. Dimensionality reduction, where you have too many dimensions to predict the outcome or patterns, you try to reduce them to a few important parameters using techniques like principal component analysis, yeah, and so on. And finding structure, that's what we are trying to do as part of the unsupervised learning, yeah. So modern semantic clustering runs k-means over the vector representations that word to vec made possible. That's what we are trying to say here. And unsupervised learning results are a little hard to evaluate. We need to treat them as hypothesis and run experiments to calculate the p-score, so that this we either accept those hypotheses or reject them. Yeah, we need to create the null and alternative hypothesis for that, and then run an experiment that will help us validate or invalidate the hypothesis that we have created. So like we said, it's hard to evaluate. There is no ground truth. It's more about understanding the patterns. But the impact is high because it validates all the downstream activities, and we need to treat these as hypothesis rather than actual if else conditions. So the honest caveat is that the model found 5 clusters, but the question is, does those 5 clusters mean something? Are they very different from each other? Are all these same? So how do we validate? By whether the structure is useful for a downstream decision, yeah, not by an accuracy score. It will accurately say we are 95% accurate, but does it mean that a downstream system will take a decision based on these 5 clusters? Yeah, so we need to frame this unsupervised work as a discovery that generates hypothesis that you can then test. Yeah, we do not present these clusters as fact. We start to validate. They are like a starting point to validate and not a finished answer. We'll look at unsupervised learning more in the upcoming sessions. We'll look at reinforcement learning also. But for today, we come to the product management layer, how the model quality is dominated by data and features. We need to understand and not be overwhelmed by what algorithm to pick and solve the problem. Why do data and features dominate and not algorithms? Because data and features are required to train the model. Because we looked at, if it is decision tree, we do the if if then or yes or no uh, branching based on the feature and its values. We looked at data for supervised learning, especially in the regression thing. So when data is in your flat tabular structures, it's more important than the algo that we are going to use, because any algo will actually work on this data. Yeah, so features are more important than the model. Whatever we give in as garbage will come out as a garbage, and that's a pm leverage. Every time we go and ask, hey, is the data ready, is the data quality sufficient, do we need to change the data quality to have better outcomes, do we have the license for the data to be used, all that questions are what pm needs to ask. Yeah, so feature engineering typically turns out the raw data into informative inputs. Yeah, from a timestamp, we could ask, hey, whether it's hour of the day, is it weekend, days since sign up, what is the actual thing, and that's pm leverage. Pm needs to tell all this. Yeah, because why does it matter in classical pm? This human craft often mattered more than the algorithm itself. Yeah, because choosing the right features for a particular model to be built was more important. Otherwise, we'll choose wrong features, the model will be built as a garbage model, and when we deploy it in production, will not have enough accuracy. So algorithm choice is usually the smallest lever, the data quality and features are the biggest. And when somebody says, hey, we have lots of data, we need to ask 4 follow-up questions. Is it labeled? Because to do supervised learning or regression, we need it to have clean labels. Is it clean, as in there is not a lot of noise, outliers, inconsistent data, all of that needs to be checked in. Is the data consistent? Yeah, is it representative of the actual population? Because we might not have data for all possible scenarios, so we need to understand if whatever we have got is representative of the bigger population. So our data becomes the sample, and we need to ensure that that smaller data represents the bigger data. And do we have the rights? Licensing, copyrights all come here, because if the data is not allowed to be touched, our whole machine learning exercise, our supervised or unsupervised exercise, goes down the drain. And the through line that we are looking at for product managers when we design these representations is a simple loop every time. Yeah. uh, Model, loss, optimizer, and generalization. Yeah. This loop keeps repeating. Yeah. What changes is who designs the representation. That's all we are saying. Yeah, representation is a lever, PM owns the data, features are product. A human judgment is required to do that. Yeah, human engineers the features by hand in classical ML. In deep learning, the features are learned from the data of their own. Yeah, but the loop never changes. It could be your supervised, unsupervised, reinforcement learning through human feedback, any of that, the loop never changes. What changes is the representation. And that brings us to this interesting crossroads on saying why this topic matters for PMs, because we stop overreaching for LLMs. We understand that, hey, this is tabular data, and we a simple gradient boosted system or boosted trees will solve the problem much cheaper, much faster, and much explainable. If for everything we use LLMs, it's costlier, there is latency, and the outputs cannot be explained from the inputs. So we need to ensure that, hey, before we approach LLMs, can we approach classic machine learning algorithms? Overfitting is your launch killer detector. Hey, have we got the accuracy correct on the evaluation and the test set, not just on the training set? Yeah, could there be a feature leakage? All this we need to catch. Choosing the metric is a product decision. Yeah, precision versus recall versus F1 score, what will we choose? Yeah, do we have labels? That gets the feasibility. Yeah, if there is no labels, we cannot run a supervised linear regression model or a logistic regression model. The traps that we are trying to avoid is on the misconceptions. We are saying more complex model, it's the better. Sometimes the sweet spot is always simpler models. Yeah, because it can explain the data that it has trained on. 95% accuracy is great. Is it on held out data, or is it on test data, validation data? We need to check. Deep learning is always best. Not really. For tabular data, boosted trees usually is the SOTA, which is state of the art model to build on. We have lots of data. Is it clean? Is it labeled? Is it representative? Is it licensed even to be used? Yeah. The algorithm is the hard part. No, the data quality and features dominate, especially in classical ML. The unsupervised found the real segments. It's true to a great extent, but we need to understand what's the ground truth, yeah, and then use a regression if required to validate them. Yeah, so unsupervised found the real segments is not 100% true. It only means that, hey, there is no ground truth. Results need validation by usefulness, by not the fact. So we need to run a regression also on top of that. Some interview questions that could be asked during interviews: explain overfitting to a non-technical stakeholder. We are saying that, hey, it's like memorizing the exam instead of learning the subject. And when we get into the another exam, we do not have answers, and that's overfitting. When would you not use deep learning? When the data is tabular in nature. Boosted trees typically are the SOTA here. They train in seconds and are easier to explain as well. That's more important. How do you choose precision versus recall? By the cost of each error. If uh, the recall for misses that hurt, precision for costly false alarms. So imagine a patient coming and we are trying to detect cancer. If we miss that, there is a there is a human loss there. The value of loss is very high, so recall needs to be perfect or very high. The precision for costly false alarms is also needs to be looked at. So a non-spam mail cannot be tracked as a spam mail. Otherwise, a good email will land up in the spam folder and user will not get access to that. So a clear balance between these two is required, but it depends on the use case and how or what will result in us choosing precision over recall. What is data leakage and why is it dangerous? Because a feature leaks the answer, and it will be brilliant offline and it will collapse in production. So we need to ensure that feature leaks do not happen. Supervised versus unsupervised, we looked at it. Supervised has labels, unsupervised does not have labels. It's to understand the pattern or the structure in the data, and which is more common, which is supervised. 90% of the time we'll look at supervised data. This is the vocabulary that we looked at today, primarily on the one idea that, hey, everything is about minimizing a loss on the training data, which is trying to generalize to unseen data or test data or validation data. The loop, the model, the loss, and the optimizer, where model tries to predict the loss, and there is an optimizer that's trying to reduce the loss so that the model can improve its weights accordingly. Supervised learning, we looked at regression versus classification, boosted trees, where it wins on tabular data. We looked at bias, variance trade-offs, and overfitting and regularization. Why is regularization important? Because if you don't regularize, it will overfit. Overfit means it will fail in the production. Then we looked at evaluation, train validation and test data. Cross validation, we looked at data leakage, precision, recall, FN. We looked at, hey, how PMs need to track or list down the metrics that we are going to track for that particular model's training, how we are going to use it for prediction. Unsupervised and PM layer, we understood that k-means and PC are hard to evaluate. Yeah, that we know. The data and the features dominate. This brings us to the conclusion. We are learning the pattern, not the answers. Yeah, that's what we learned in track B, part 3 of machine learning 1, supervised and unsupervised learning.